Welcome to a time when farming was invented, not updated. These machines solved problems before technology existed. Simple, brilliant, unbreakable. Modern farming still follows their designs. This isn't old equipment, it's the blueprint. Number 1. Jethro Tull's Seed Drill, 7001. Long before precision ag became a marketing term, the seed drill introduced the central promise of precision planting. Put seed where it has the best chance to thrive, not where it happens to land. In 1701, English agricultural pioneer Jethro Tull developed a seed drill designed to sow seed in orderly rows at a controlled depth rather than broadcasting seed by hand. The key breakthrough wasn't just speed, it was repeatability. A seed drill uses a hopper and a metering mechanism to deliver seed through tubes or channels into the soil in a more uniform pattern than hand scattering can achieve. That row and depth control concept is exactly what modern planters still chase, just with better materials and finer control. Today's row crop planters use sophisticated meters, vacuum, finger pickup, etc., downforce systems, and closing wheels. But the logic is still Tull's logic: consistent placement, consistent spacing, consistent depth. When modern planters talk about singulation, spacing accuracy, seed-to-soil contact, and emergence uniformity, they're basically refining the same objective that the seed drill introduced: reduce waste, reduce competition between seedlings, and make plant populations predictable. The seed drill also normalized a deeper farming habit: straight rows. Rows make cultivation, weeding, later mechanized harvesting, and field management more systematic. Even modern guidance systems, auto-steer, assume that rows are the organizing geometry of the field. The seed drill didn't just plant seeds, it reshaped the way farms were laid out and managed. In that sense, modern farming still copies the seed drill every time it treats planting as an engineering problem, one that can be optimized by controlling how seed enters the soil. Number 2. The mechanical reaper, 1830s. If you've ever watched a modern combine header glide through wheat, you've seen the mechanical reaper's legacy. In the early 19th century, harvesting small grains required enormous labor, cutting with scythes, gathering, binding, and hauling. The mechanical reaper mechanized the cutting stage, turning what had been a hand skill into a machine process. Cyrus McCormick is strongly associated with a workable reaper design dating to 1831, and by the mid-1800s, reapers were transforming grain harvesting across large areas. The reaper's core idea is surprisingly modern: a cutting mechanism paired with a way to manage the flow of crop into the machine. Early reapers used a reciprocating blade, sickle bar, and a reel to guide standing grain toward the cutter. That combination, a reel controlling crop flow plus a cutter doing the separation, is still visible on many harvesting platforms today. Modern headers may use different systems depending on crop: flex heads for soybeans, draper heads, rotary cutting systems in some cases, but the engineering purpose remains the same: present the crop to the cutting edge cleanly, keep the feed steady, and minimize loss. What people often forget is that the reaper wasn't just a machine. It forced standardization in harvesting timing and field operations. Once cutting became faster, the bottleneck shifted to other steps: threshing, transport, storage. That pressure is part of what pushed the industry toward combined harvesting systems later on. So even though a mechanical reaper looks primitive compared with a combine, it helped create the workflow logic that combines perfected: mechanize one stage, then mechanize the next, until multiple stages can be integrated into one pass. Modern farming still copies the mechanical reaper every time it assumes that harvesting starts with a controlled mechanical cut and a managed crop flow into a processing system. That's the reaper's blueprint, just upgraded. Number 3. Check row and early row planters. A lot of people assume row spacing and uniformity came from modern planters. In reality, planters were obsessing over seed metering and spacing long before electronics. Check row planters, often associated with wire check systems, helped standardize plant placement so fields could be cultivated in both directions. A big deal before herbicides became dominant. John Deere's long-running planter lineage includes famous models like the number 999, and historical accounts describe improvements aimed at accuracy and ease of adjusting seeding rates. What modern farming still copies here is the mindset that planting is not merely dropping seed, it's metering. Early planters used plates and mechanical mechanisms to pick up kernels and release them at intervals. That's conceptually the same job a modern seed meter performs, whether it's vacuum-based or finger pickup. Even the idea of changing population on the go, something we now do with variable rate drives, has roots in the older desire to adjust seed rate without stopping, because time and consistency mattered even then. Also, these older planters made row cropping scalable. Once you can plant in consistent rows, you can cultivate more efficiently, harvest more systematically, and plan rotations and equipment widths. Modern planters and drills have become faster and more precise, but they still depend on the early planter tradition: predictable row geometry, predictable seed populations, and mechanical reliability. So when modern agriculture celebrates stand uniformity and emergence timing, it's building on a foundation laid by early row planters that turned planting into a controlled mechanical process rather than a rough distribution of seed. Number 4. The Farmall Regular Row Crop Tractor, 1924. Tractors existed before the 1920s, but row crop farming demanded a different kind of tractor, one that could straddle rows, cultivate between plants, and maneuver in tighter spaces. The Farmall Regular, introduced in 1924, is widely recognized as a major step in making the row crop tractor a practical, commercially successful category. What made the row crop tractor concept so influential wasn't simply the engine, it was the geometry. The ability to work between rows, provide good visibility of the crop area, and adapt to row spacings helped tractors become true multi-purpose field machines rather than just heavy pullers. This is the quiet logic behind modern row crop tractors: clearance, maneuverability, and a design that assumes the field is laid out in rows that must be respected and serviced repeatedly during a season. Modern tractors look different: cabs, emission systems, complex transmissions. But the row crop category still carries that same idea. The tractor is not just a source of draft power, it's a platform for repeated row-based operations: planting, spraying, cultivating, side dressing, harvesting support. The Farmall era helped push tractors into that role, which is why the row crop tractor remains a distinct type even now. In other words, modern farming still copies the Farmall Regular's underlying insight. If crops are organized in rows, the tractor's body and stance must be organized around those rows too. Number 5. The Ferguson 3-point hitch, patented 1926. Ask a farmer what 3-point hitch means, and they'll treat it as basic vocabulary like it was always there. It wasn't. Before this system took over, most implements were pulled using drawbars like trailers. The Ferguson 3-point linkage, patented in 1926, became foundational because it created a rigid, controllable connection between tractor and implement and enabled better transfer of forces, including draft control concepts that improve traction and safety. Modern farming still copies the Ferguson system constantly because 3-point hitches became a global standard for mounting and lifting implements. The reason this matters isn't convenience alone. Mounted implements change the tractor's dynamics. Weight transfer, stability, turning, and depth control are all affected by how the tool is attached. A 3-point hitch allows the tractor to lift, carry, and precisely position equipment. It also encourages an entire ecosystem of implements designed to match standardized hitch categories and geometry. You can see the Ferguson idea in everything from a compact tractor carrying a box blade to high-horsepower tractors lifting heavy-mounted tools. Even in operations where drawbar pulling still dominates, big trailers, some large tillage, the 3-point hitch remains central for many tasks because it integrates the tractor and implement into one working unit. If the seed drill taught farming to love rows, the 3-point hitch taught farming to love standard interfaces. Today's quick hitches, hydraulic top links, and implement control systems are all refinements of the same basic architecture, a stable triangular linkage that makes implement handling safer, faster, and more controllable. Number 6. Early self-propelled harvesters and auto headers, 1911-20s. Combines feel like the most modern machine on the farm, but their conceptual leap is older than many people realize. Sources commonly note that Holt produced a self-propelled harvester as early as 1911, and that in 1923, the Sunshine Auto Header in Australia was among early center-feeding self-propelled harvesters. In the same general period, Gleaner patented a self-propelled harvester with improvements in grain handling. What modern farming still copies here is the fundamental combine concept: integrate multiple harvest stages into a single moving machine. Even when early machines were imperfect, they proved the principle that a self-powered platform could cut standing crop and manage material flow through processing components while moving across the field. That core one-pass harvesting architecture is what every modern combine is built around, whether it's a conventional walker machine or a rotary combine. These early self-propelled harvesters also pushed the industry toward better crop feeding and grain handling, problems that remain central today. Modern combines obsess over feed consistency, minimizing grain damage, reducing losses, and keeping throughput high under variable crop conditions. The sensors and automation are new, but the engineering problem is the same one those early inventors wrestled with: how to move crop through a machine smoothly while separating grain efficiently. So when modern farming talks about harvest efficiency, it's still working within a framework established by early self-propelled harvesters, machines that most people have never seen in person, but whose blueprint lives on every harvest season. Number 7. The Allis-Chalmers roto-baler, 1947. Round bales feel normal now, but round baling didn't begin with the big modern balers you see today. A key milestone was the Allis-Chalmers roto-baler, introduced in 1947, which produced small round bales and proved that rolling forage into cylinders could work as a practical system. Historical summaries note that large numbers were sold before production ended in 1960. Modern farming still copies the roto-baler's central idea, a rolling chamber that forms and compresses a cylindrical bale. Modern round balers are usually making much larger bales, and the mechanics evolved. Belt systems became a defining approach in modern large round balers. But the roto-baler matters because it established round baling as a workable alternative to traditional loose hay handling or small rectangular bales. Round bales changed the labor math of hay. Once you can produce a bale shape that sheds water reasonably well and can be moved with mechanized loaders, you reduce dependence on large crews and simplify storage and feeding logistics. Today's round balers add net wrap, density controls, moisture sensors, and high-capacity pickups, but the workflow is still the same. Gather windrow, roll into a tight cylinder, bind it, drop it, move it with equipment. The roto-baler is forgotten, mostly because its bales were smaller than the ones we associate with modern baling. Yet it's the proof-of-concept machine that showed the world round baling was not just possible, but commercially viable, an idea that the entire hay industry still copies. Number 8. Center pivot irrigation, late 1940s. Those huge green circles you see in satellite images aren't just pretty patterns, they're the signature of center pivot irrigation. The system is strongly associated with farmer inventor Frank Ziebach, who developed a prototype in 1948 and applied for a patent in 1949 for what was called a self-propelled sprinkling apparatus. This became the center pivot irrigation system. Modern farming still copies center pivot irrigation because it solved a massive practical problem: how to distribute water more evenly over large areas without constantly moving pipes and sprinklers by hand. A pivot rotates around a fixed point, carrying water along a long pipeline supported by wheeled towers. The result is repeatable coverage, scalable field irrigation, and predictable water application patterns. Even when modern systems add variable rate irrigation, better nozzles, pressure regulation, and remote controls, the underlying machine geometry stays the same. One pivot point, rotating coverage. The machine doesn't just irrigate, it reshapes farm planning. Field shapes, crop planning, and infrastructure often adapt around pivot circles because the efficiency is so high. In that sense, center pivot irrigation is one of the clearest examples of modern farming still copying an older machine. The materials, motors, and controls evolve, but the original mechanical concept remains a dominant standard across irrigated agriculture. Number 9. The early no-till planter with fluted coulters, 1960s. No-till farming feels like a modern sustainability movement, but it required a very specific mechanical breakthrough: equipment that can place seed into residue without full-width tillage. One major milestone frequently cited in no-till histories is the introduction of a fluted coulter no-till planter by Allis-Chalmers in 1967, described as an early commercially successful approach. Modern farming still copies the physical logic of those early no-till planters. The challenge is straightforward but brutal. Crop residue is tough, soil may be firm, and the seed still needs consistent depth and seed-to-soil contact. Coulters and openers became the front-end solution. Cut residue, open a slot, place seed, and close it properly. Today's no-till and strip-till planters may use different coulter styles, row cleaners, advanced downforce systems, and closing wheel configurations, but the architecture remains the same: cut, open, place, close, all without full tillage. This is why older no-till hardware deserves more credit than it gets. It wasn't just an attachment, it created an entire equipment category and proved that large-scale cropping could reduce tillage passes if the planter could do its job in residue. Modern conservation agriculture is full of software and agronomy improvements, but mechanically, it still depends on the same breakthrough those early machines made practical. Number 10. Pulsator. Vacuum milking machines 1890s. Modern dairies can look futuristic. Automatic milking systems, sensors, herd management software. But the physical act of machine milking still relies on a core 19th century breakthrough, pulsation. Historical sources describe how, around the 1890s, innovators developed pulsators that alternated suction levels to extract milk while protecting teat tissue and circulation, an essential difference from continuous suction. Developments like teat cup design and pulsation systems helped make machine milking viable and eventually widespread. Modern farming still copies this because the biology doesn't change. A milking machine must mimic the rhythmic action of a calf, apply suction to draw milk, then release to allow circulation and prevent injury. Whether you're using a bucket milker, a pipeline parlor, or a robotic milker, the system still depends on controlled pulsation and a teat cup interface that can seal and release appropriately. What's forgotten is that the critical innovation wasn't automation. It was understanding that milking needed a pulsating vacuum, not constant suction. Once pulsation became standard, the dairy industry could scale labor, improve consistency, and design barns and parlors around machine milking workflows. Modern robots add identification, teat detection, and data tracking, but underneath the intelligence is the same pulsation principle that made machine milking humane and effective in the first place. So every time a dairy system cycles its pulsators quietly, thousands of times a day, it's repeating a breakthrough that dates back well over a century. These machines never disappeared. They evolved. Every modern farm still carries their DNA. Trends change. Technology upgrades. But true innovation never dies.